Dr. Tai Hoang Le. He's associate professor at the University of Mississippi, and today he will present talk on arithmetic Ramsey theory. So please, your time, Hoang.
All right, yeah, so it's a pleasure um, to give a talk, and thanks for the invitation. So today I'm gonna talk I'm gonna talk about arithmetic Ramsey theory, so you will see what it is about. So what I like about this area of mathematics is that so the statements um, um, are very like, elementary and easy to understand. But on the other hand, so it involves many different areas of mathematics, and it is very interesting. So first, so what is Ramsey theory? So you probably have heard about Ramsey theory. So the basic principle in Ramsey theory is that so if you have a very large system, then there must be a structured subsystem. So you can always find structures if you have sufficiently many objects. So actually, so I like my talk to be interactive. So I will ask you sometimes. I will ask you questions. So can you think of any very simple yet very powerful principles in mathematics in this spirit? Can you find an example for this phenomenon?
The structural subsystem is kind of subspaces, right? Got that.
Yeah, so we are very vague, so we don't mean anything by that. So I don't define what is a system and what is structure. So it's up to your imagination. So can you come up with an example in this spirit?
I think like more complexly, it reminds me of like a matrix, like we're doing in linear algebra, and having like a subset of that, or like really simply, it reminded me of just like a least common factor. Like if you have a large number, there's smaller factors inside of it. That's what it reminded me of.
Yeah. So what I mean is that we have not just one object, but we have a bunch of them. Let's say if we have many guys, then I can say something interesting. So I think so. This is one of the most basic principles in all of mathematics, right? And it's very simple. So if you have more pigeons than holes, then you can find more than one pigeons sharing the same hole. So that's the pigeonhole principle, right? So it's a basic principle in combinatorics, but it turns out to be very useful, and actually it's extremely powerful. So here's another example in the same spirit. So so when you take real analysis, then there's the Bolzano-Weierstrass theorem, so which says that any bounded sequence of real numbers has a convergent subsequence. So this is a manifestation of the same principle, and actually you can prove this using the pigeonhole. Okay, so I don't know how to. So this is my first time using Teams, so I don't know how to draw a picture on my screen. But it just so you take an interval, right, and you divide it in half. And so half of the interval must contain infinitely many elements of your sequence, right, by the pigeonhole principle. And you take the previous half and you divide it in half, then there is a quarter which contains infinitely many elements of the sequence. And if you keep doing that, then you have a convergent subsequence. So that's the proof of the Bolzano-Weierstrass theorem, and it just uses the pigeonhole principle. Okay, so Ramsey's theorem, Ramsey theorem is named after Ramsey's theorem, and what does it say? So if Kn denote the complete graph on n vertices, so you have n points, and you connect every single pair between them, so you have a complete graph. And Ramsey's theorem says that there exists a number n. So if the number of points is large enough, and you color the edges of your graph by a fixed number, say 10 colors, then there is a monochromatic KK. So monochromatic means that all the edges of that graph have the same color. So if fix a number K, say 7, right? And if your n is big, and if you color the edges of Kn by 10 colors, then you can find a copy of K7. All of whose sides, all of whose edges have the same color. So for example, so here's a special case of Ramsey theorem. So I guess like probably most of you are familiar with this. So if you take any 6 people, then you can find 3 people who mutually know each other or who mutually don't know each other, right? So we are coloring the graph on 6 vertices with 2 colors. So if 2 people know each other, then we color them by 1 color, say red. And if they don't know each other, then we color them by, say, blue. So this statement says that in case 6, if you color the edges by 2 colors, then you can find a red triangle or a blue triangle. All right, so any questions so far? So that's Ramsey's theorem, which is about graphs and things like that. But we're not actually talking about this because I like the integers. So I like the same phenomenon, but when we talk about large subsets of the integers. And what do we mean by large? So there are 2 kinds of results in arithmetic Ramsey theory. So partition result says that if you color or partition the integers into finitely many classes, then one of the colored classes contains a nice structure. So in other words, we can find a monochromatic structure. And the second kind of result is density result. So which says that your A is dense. So I will define it in a second. If your set A is dense, then your set contains a nice structure. And what do I mean by dense? Okay, so let us introduce some notations. So this n in brackets means the set of all integers from 1 to n. And I define the upper asymptotic density of my set as the lim sub when n goes to infinity of the proportion of A in the interval from 1 to n. Right. So if I take this proportion and I take the limit lim sub of that when n goes to infinity, then I call it the density of A. And I say that A is dense if the upper asymptotic density is positive. So for example, all the even numbers have density 1/2, right? Yeah, because basically you can find an even number for any 2 integers. So the second kind of results, the density results, always imply a partition result, because if you have a partition, so Z is the union of the sets AI, then some of those sets AI has density greater than 1/R. Right. So whatever is true for densities is also true for partitions. But on the other hand, so not all partition results have a density counterpart. All right. So any questions so far? So Ramsey's theorem was so appeared in 1928, but actually the first result so let's now look at some early results in Ramsey theory. And so the first result is actually due to Hilbert in the 19th century. So it says the following. So if you color the integers with R colors, then for any K, then you can find a monochromatic set of the following form. So it fix some x naughts and x1 and xk, and it makes sums of this form. So x naught is there, but for hi takes a coefficient of 0 or 1. So you can think of this as the analog of a cube of dimension k. And this is not exactly a cube, but it's a translate of a cube because we translate this thing by x naught. Right. So Hilbert says that however you color the integers with our colors, then there is always a translate of a cube of dimension k, which is monochromatic.
What is x0 in this case?
It's something. So it's an existence theorem. I don't know what it is. I cannot specify what it is. So the theorem says that there exists x naught and x1 and up to xk.
And when you are talking about R colors, that means you consider some partition, right?
Yeah, right.
Of Z, yeah. You know, it's just, you know, you have R mutually disjoint, right? Subset.
Yeah.
Okay.
Yeah, that's right. Yes. Yeah. So coloring. So I wouldn't say some. So sometimes I say coloring, and sometimes I say partition, but they are the same. They are exactly the same way to. There are exactly two ways to say the same thing.
But this partition is nothing related to kind of, you know, equivalent classes. No. Just random partition.
Yeah. Right? So the part is that the partition is arbitrary. So yeah, we can do like whatever we like, and it turns out that we always have a structure in one of the partition classes.
Okay.
Right. So here's a concrete example. So if you take the integers and you color or partition it into say 10 sets, then there are x, y, and z. So I don't know what they are, but there exist x, y, and z such that these numbers have the same color. Right. So this is a translate by x of a cube spanned by y and z. So it's a cube of dimension 2. Right. Okay. So nowadays, so if we see this theorem, then we say, wow, so that totally makes sense, right? But yeah, but it's not like, so 100 years ago, it was not completely natural. Who would think of this? Who would think about monochromatic cubes? So the motivation for Hilbert was that, so he used this as a lemma to prove the following theorem. So Hilbert's irreducibility theorem. So if you have a polynomial in 2 variables and with integer coefficients, so which is irreducible in this ring, z of x and y, then you can fix y, right, to be a fixed number n, and you can do that for infinitely many n. And you can fix y in such a way that the resulting polynomial, so which is now a polynomial in x. So this guy is irreducible in z of x. All right. So any questions?
Oh, well, what is the definition of irreducible polynomial?
Yeah. So you're asking about the deduction from this lemma to that theorem, right?
No, the definition.
Oh,
what does mean? You know,
it cannot be expressed as the product of 2 guys.
Okay.
Yeah, nice. So it's like prime numbers, but for a ring.
For a ring, right? Okay.
So this guy cannot be expressed as the product of 2 other polynomials.
Thank you.
Yeah. So so I was afraid that you asked about the deduction because so I never thought about it, and then I look it up, and it turns out that deduction is highly non-trivial. It's not like you can deduce it in a single line, so you have to work. So it's non-trivial to deduce this theorem from this lemma. Okay, so this is probably the first theorem in this area. And next one is due to Schur. So Schur, so it's the same Schur. So if we see, if we take linear algebra, so it's the same Schur in linear algebra representation theory. So Schur worked in many different areas of mathematics, so including number theory and combinatorics. So Schur's theorem says the following. So if you color or partition the integers, let's say the positive integers, by our colors, then you can find three numbers, x, y, and z, in the same color class, such that x plus y is equal to z. Right? So x, y, and x plus y have the same color. So yeah, so x, y, and x plus y is a cube of dimension 2, right? But the difference between this theorem and the in Hilbert's theorem is that we do not translate a cube. So we already have a cube and we don't translate it. Okay, so like, why did Schur care about this theorem? So so the reason why Schur was interested in this theorem was that he studied Fermat's last theorem, not in the integers, but in cyclic groups. So we know that this equation, so Fermat's theorem says that the equation x to the m plus y to the m plus z to the m does not have equations in z, right? But what if what if we ask for solutions in the cyclic group z over z, pz? Or in other words, we're asking for congruence modulo p. Then can we find a solution? And it turns out that yes, we can. And so that's the result of Schur, and he used the above theorem to deduce this theorem. Any questions? Okay, so let's now prove Schur's theorem quickly using Ramsey's theorem. So I want to show that if I have an R coloring of the integers, then I can find three guys, x, y, and z, such that x plus y is equal to z. And I don't need infinitely many integers. I can only work with integers from 1 to n when n is a large number. So if I have a coloring of these numbers, then I can create a coloring of a graph. So my graph is the complete graph on n vertices. And I give the color of the edge ij, where I is less than j, the color of the number j minus I. Right? So if we have a coloring of these number integers, then we have a coloring of the edges of the graph. And by Ramsey's theorem, so I know that if n is sufficiently large, then I can find a monochromatic triangle, K3. And the vertices of that triangle are numbers A, B, and C. So let's now look back the way we color this graph. So because I give the color of the hij, the color of the number j minus I. So that means that those numbers b minus a, c minus b, and c minus a have the same color, because these are the colors of the monochromatic triangle. And I have found a Schur tuple, because c minus b plus b minus a is equal to c minus a. So this is the proof of Schur's theorem. So any questions? So this pretty quick, right? But so you may ask, so Ramsey's theorem was proved in 1928, and Schur's theorem was from 1916. So how could Schur have known this proof? And so Schur's original proof is different from this. So this is the standard proof of Schur's theorem, but Schur proved it in a different way, but his proof was also elementary. So another result, another early result is van der Waarden's theorem, and which says that if we color the integers or positive integers by finitely many colors, then for any k, you can find a monochromatic non-trivial arithmetic progression. So what is an arithmetic progression? An arithmetic progression is a set of the form a plus d, and a plus k times minus 1 times d. So we have k numbers which are equally spaced by a number d. Right. So this is highly non-trivial because a coloring is just arbitrary. So you color the integers however you like. But an arithmetic progression is a very structured set. And it turns out that we can find such structure inside any coloring. So that's quite surprising. So van der Waarden was the first one to prove it, but it was conjectured previously and independently by Baudet and Schur as well. So again, so Schur asked this question because he was motivated by another number theoretic question. Any questions? All right, so at the beginning, so I said that there are two types of results. So density results and partition results, right? And density results always imply partition results. So let's now look at these theorems and ask if we have density counterparts. So recall that Schur says that if you finitely color the integers, then you can find x, y, z having the same color such that x plus y is equal to z. So is there a density version of this theorem? So in other words, if A has positive density, then you can find three numbers x, y, z in your set such that x plus y is equal to z. What do you think? Is there a density version of this theorem? So the answer is no, because if I take A to be the set of odd numbers, then clearly my set has density 1/2. And I cannot find a solution to this equation in my set of odd numbers, right? So let's now look at Hilbert's theorem. So Hilbert says that if you finitely color the integers, then for any k, you can find a monochromatic translate of a cube of dimension k. So what do you think? Is there a density version of this theorem? Or in other words, can I find such a set inside any set of positive density? So it's hard to see, but the answer is yes. So it's actually not quite hard to prove it. So we know that there is a density version for Hilbert's theorem. And let's now look at van der Waarden's theorem. So which says that if you finitely color the integers, then for any k, you can find a monochromatic non-trivial k-term arithmetic progression. So it turns out that a density version of this result exists, and that's the celebrated Ceremonies theorem. So yeah, so we will talk more about this. So do you have any questions so far?
So it seems to me that to find a density version is also a good. It is also a good activity, right? And is there any meaning about that? I mean,
No, we just do that because we like it. Just like everything, like not everything, just like many things in mathematics.
no,
we just
I agree, but I just try to understand the relation like between the
also the
density
reason
version
is
and that
that
one.
a density result always imply a partition result,
Yeah.
but the
So
other direction is not true.
okay.
So when you have a result, then you ask, can we do better than that, right?
Mm-hmm.
And sometimes you can, and sometimes you can't. So van der Waals theorem is not too like difficult. I mean, so you have to come up with like really like ingenious ideas to prove it, but nowadays, so you can prove it in say 1 page. And if you are a smart high school student, then you can understand the proof.
And this only in Z plus, right? So is it
Yeah. So yeah.
like is there any generalized version for Z or?
So I say these theorems for Z plus, but they're all true for Z, and they are all equivalent. So it's true for Z, then it's true for Z plus, and vice versa. So
I see.
yeah, it's just a matter of routine checking.
Mm-hmm.
All right. So any other questions? All right. So let's now talk about more density theorems. So so probably the first result in this area was due to Roth, so who proved the a special case of Ceramides theorem for 3-term arithmetic progressions. All right. So if I so again, so I put Z over here, but if I put Z plus over here, then that's also true, and vice versa. So yeah, there's no real difference between Z and Z plus. So if I take a set A of positive density in the integers, then A is guaranteed to contain a 3-term arithmetic progression. So like I said, so this area, I like this area because I mean, so the first of this statement is very easy to understand, but furthermore, there are multiple approaches to a single thing. So today, so there is a lot of different proofs of this theorem from different areas. So Roth's original proof used Fourier analysis, and more specifically circle method, which is a method in number theory. And Ceramides was able to prove this theorem using combinatorics. And a few years after that, so Furstenberg came up with an entirely different approach using ergodic theory. And well, so you may think that this is the end of the story, but even nowadays, you can still come up with new proofs of this theorem. So it's still a yeah. So I will talk more about that later. But so it's in an active problem. All right, and these people are all famous. So Furstenberg just won the Abel Prize 2 years ago, and Ceramides won the Abel Prize 10 years ago, and Roth also won the Fields Medal in '54 for something else. But this was his second favorite result. So this is the special case of Ceramides' theorem for 3-term arithmetic progressions. So Ceramides says that, well, the same is true if, for arithmetic progressions of length k, and this is considerably more difficult than Roth's theorem. So Ceramides first proved this theorem in 1975 using graph theory. So his proof was very complicated. So I was at a conference where someone made a joke by saying that the number of people who understand Ceremoni's proof is pi. And someone pointed out that pi is not an integer. And then he corrected it by saying that it's the integer part of pi. And so Furstenberg reproved this theorem using an entirely different approach, using ergodic theory. And and after that, so 20 years after that, so Gauss gave yet another proof using a totally different approach. And well, that's not the end of the story, because after that, we also came up with another proof using hypergraph. And even like recently, so there is a new proof by Polymath, so which is a collaboration on by multiple people, so led by Tao and by Gauss. Any questions? So so let me show you yet another theorem in the same spirit. So if I take a dense subset of the integers, then I can find two numbers, a and a prime, in the set, which differ from each other by a perfect square. So again, this is very surprising, because what is a dense set? It's just any set, right? As long as it has sufficiently many elements. So you have a set and which has a lot of elements. And it turns out that you can find two elements in the set which differ by a square. So again, so there are multiple approaches to this theorem. So Shakuzi's paper appeared after Furstenberg, but I think he proved it before Furstenberg. So his proof again uses the circle method of Fourier analysis. And so Furstenberg proved this using ergodic theory. So these proofs are like nice, but they are not elementary. So it turns out so recently, so there is a elementary proof by Green and Tao and Ziegler, and the proof is elementary. So it doesn't use any anything beyond high school mathematics. And if you are a bright high school student, then you can understand the proof. But of course, it's so coming up with the proof is a different matter. Any questions? So okay, so let's try to modify this theorem a little bit. So I know that A contains a difference, which is a square. So what is special about these squares? So can you replace it by other things? So can I replace it by n squared plus 1? So what do you think? So if I have a dense set, so which means that its positive density, which means that its upper density is positive, then am I guaranteed to find two numbers in the set whose difference is of the form n squared plus 1? What do you think?
Seems like not impossible, right? Not possible.
Uh,
Sometimes.
Yeah, that's true. Right? So, but can you give an example? So if we take the set of all multiples of 3, right? So the differences of A stay in the same set, right? So difference of two multiples of 3 is also a multiple of 3, but we can never find a multiple of 3 of the form n squared plus 1. Okay, so so that means that you cannot put whatever you like in here. So it has to be something special. So so if you want to eliminate counterexamples like P(z) or d times z, so a necessary condition is that for any d, for any positive integer d, so there exists an n such that d divides h of n. Right. So this is this is clearly a necessary condition to avoid this kind of counterexample. And well, so what's quite surprising is that this condition is also sufficient. Right. So instead of n squared, you can put any polynomial you like with this property that for any d, you can find a value of the polynomial which is divisible by d. So what are those polynomials? So for example, n squared minus 1, right? So if you give me any number like 17, then I can find n such that n squared minus 1 is divisible by 17. So I can take n to be 18, for example. And in the same spirit, I can take any polynomial having an integer root, right? Meaning that h of n is equal to 0 for some n. And of course, if 0 is divisible by any integer d. But this example is a bit boring, right? So you solve the problem that your h of n is divisible by d by saying that it's equal to 0. So here's a more exotic example. So this polynomial doesn't have any integer root, but it has the property that it is divisible by any d. So if you give me any d, then I can find an n such that this thing is divisible by d. Yeah, so coming up with examples like this is actually non-trivial mathematics. Okay, so instead of polynomials, then you may ask, so everyone loves primes, right? So how about the primes? Can I put expressions involving primes instead of n squared? And well, the answer is yes. So instead of n squared, you can put p minus 1 or p plus 1 where p is prime. So in other words, I can find two elements in A whose difference is of the form p minus 1 where p is prime. And you may ask, so why do we put p minus 1 or p plus 1? So can we just put p? Well, so p is not possible because of the same kind of abstraction. So if you take a to be multiples of 4, for example, right? Then a minus a consists of multiples of 4, and you cannot find a prime number which is divisible by 4. But on the other hand, you can find a prime number p such that p minus 1 is divisible by 4. And yeah, so for that reason, so these are the only translates of the primes having this property. Any questions? So far I have talked about statements about that set of the integers or positive integers, but most results have an equivalent and finite version. So for example, so here's a reformulation of Szemer's theorem. So remember that this denotes the set of integers from 1 to n. So Szemer's theorem says that if we try to avoid k-term arithmetic progressions, then the size of your set must be less than O of n, meaning that if we divide the size of A by n, then it will go to 0 when n goes to infinity. And here's another equivalent reformulation of the Furstenberg-Sarkozy theorem. So if you want the differences to avoid the squares, then the size of your set has to be small compared to the size of n, which is the length of the interval. So we have seen multiple approaches to these theorems. So ergodic methods can prove very general results, but on the other hand, they do not give bounds. And on the other hand, so Fourier analytic methods are capable of giving bounds. And what do I mean by giving bounds? So I have like concrete shapes of these numbers, ln O of n. So so let's take Ross' theorem. So we says that if a set A does not contain non-trivial arithmetic progressions, then the size of A is ln O of n. So Ross' original proof gives this bound. So the size of A is smaller than some constant times n over log of n. Right. So so it took a long time until we reached this bound. So for any epsilon greater than 0, so the size of A is smaller than n over a power of log, and the power is slightly smaller than 1. Right. So instead of a log of n, we have log n. And it also took considerable effort to get past this exponent of 1. So now we can do better. So we can do n over log n to the 1 plus c for some constant c greater than 0. So this was an achievement, because what is special about number 1? Well, so if we know, because the density of the, so if we don't want to talk about dense sets, you want to talk about sparsal sets like the primes, so which are also very interesting. And so the primes have density n over log n, right? So if we have a power greater than 1, then you will be able to talk about the primes. So let's take Ceremony. So so Ceremony says this. So if we want to avoid k-term arithmetic functions, then the size of your set A has to be ln O of n. And Gowers proved this awesome bound. So before that, so the bound was terrible, but Gowers proved this. And this was one of the results for which he was awarded the Fields Medal in '98. And let's take the Furstenberg-Sarkozy theorem. So if so if the differences avoid these squares, then the size of the set has to be ln O of n. So Sarkozy's original proof gives this bound. So size of A is smaller than some constant times n over some power of log n, when the power is a bit less than one third. And we can do much better than this. So so Pin, Steiger, and Ceremony prove that the size of A is smaller than n over log n to some power. But what is important is that this power goes to infinity, right? So it's much better than one third. Okay, so this is very good, but the proof was very difficult. And then recently, so Bloom and Maynard proved this bound. So it looks similar, but it has one less log. So in Pin, Steiger, Ceremony bound, we have 4 logs, and here we have only 3 logs. Yeah, but this is already very good. And Maynard just won the Fields Medal this year. So I have 5 minutes left, right? Yeah, so I have 5 minutes left. So yeah, I will talk now. I will talk about some technical details. And Yeah, but if you don't want to see the details, then just let me know and we can just stop here. Yeah, maybe I will just talk about. So I wanted to talk about two things. So the Fourier analysis approach and the ergodic theory approach. Okay, so maybe I will talk about. So this is the Fourier analysis approach by Roth. So which is I mean, it's not elementary, but it's also concrete. But Furstenberg uses Furstenberg's approach uses ergodic theory, so which is more abstract. Okay, so I will talk about this. So let's recall Roth's theorem. So which says that if A has positive density, then A contains a three-term arithmetic progression with common difference D. So this can be written as the intersection of A and A plus D and A plus 2D is not empty. So this is a statement about the integers. But Furstenberg's insight was to translate this theorem or this statement to a statement about measure preserving systems. So what is a measure preserving system? So a measure preserving system consists of a probability space, right? So you have a space or just any set on which you have a measure, and the measure of the whole space is 1, right? So that's a probability space. And beside that, we have a measure preserving transformation. So what is a measure preserving transformation? It's a map from the space to itself with the property that the measure, with the property that the inverse image of any set has the same measure as the set, right? So that's, well, so let's take an example. So for example, we take X to be the torus, and mu is the Lebesgue measure on the torus, and T is just a translation. So you have something on the circle, right? And you translate it. So clearly it is, this transformation is measure preserving. So, and this is about the simplest kind of measure preserving systems. Okay, so how is this related to the integers? So in the integers, so we also have some kind of measure, right? So which is the upper density. So it is also, it's very close to a probability measure. So the upper density of everything is 1. And it has this property that if you take the union of two sets, then the density of the union is less than or equal to the sum of the densities. But that's about it. So we don't have equality, and which is so when A and B are disjoint, so, right? So which is one of the properties of the of probability. And our map, so on the integers, we have this map. So we translate everything by 1 to the right. So this map is also measure preserving in a sense, because if you translate a set by 1, then the density is not changed. So the integers and this density is not a probability measure. So Furstenberg says that, well, so instead of looking at the integers, then you can look at measure preserving systems. And here's the statement. So here's a statement which is equivalent to Roth's theorem. So if you are in a measure preserving system, and if you start with a set E, whose positive is positive, then you can find an integer D such that these 3 sets, so E itself and its translate, well, not translate, but yeah, so pre-image by T to the D and pre-image by T to the 2D. So these 3 sets have positive. So the intersection has positive measure. So this statement is even more complicated than the original statement. So what is the advantage of working with this? So the advantage of working with general measure preservation systems is that we can sort of simplify our system, right? So I have a very abstract system. I don't know what it is, but hopefully I can simplify it to simpler systems, and in which I can say nice things. And so if we look at the intersection of two guys, then it's not easy. I mean, it's not difficult. I mean, it's quite easy to show that well, we do have this for two guys. But if we insist on the intersection of three guys, then that's not trivial. Okay, so yeah, I guess I have -1 minute left. So so you can reduce. So if you want to prove this, then you can reduce to a nice system. So you can reduce it to this kind of measure preserving system. So instead of this, we have a group, a compact group, which is so compact groups are easy, very well understood, and so we know what these things are, and we can show that it is positive. All right, so yeah, so let's end the talk here.
Yeah, thank you very much. Thank you, Dr. Lei, for the talk. Do you have any questions for our speaker? It seems to me that all techniques are very difficult, right? And you mentioned several times in your talk is that many mathematicians in this direction got field medals.
Yes, yeah. So it's a good thing to work in this area.
Yeah, interesting.
Yeah. So yeah, so I didn't say this, but you have like so many approaches to this theorem. So like all of them are deep, and all of them open up future fields of research, right? So for example, so Furstenberg, by his proof, so he opened up a new research area, and same thing for Gowers.
Interesting. But like in one of the last results says about refinement, and you said the guy who got field medal this year.
Yeah. So I think this result is like nice, but I think it's not like good enough for getting the Fields medal. So he got the Fields medal for his other work, but not
for other works.
particular result.
I see.
Yeah.
Okay. Yeah, interesting. Do you have any questions? Okay, if not, so let's thank our speaker again for his interesting talk. Okay, and and we see you next week. Yeah, thank you, Dr. Lei.
All right.
And let me stop recording.